everyone, and welcome back. Today we're going to be continuing our exploration of a nice little investigation of stochastic processes and discuss what it means for a stochastic process to be a Markovian process. Some people just say a Markov process. But again, what is a stochastic process in case you've never heard of this word before? You can view a stochastic process as just a sequence of random variables xt, where xt ranges from the set t to the set s, where s is called the state space of the stochastic process. And the set t doesn't necessarily have to be a discrete set. It can be a continuous or an uncountable set if it desires to be. And if it's discrete or countable, some people will call it a discrete stochastic process, and if it's uncountable, some people will call it a continuous stochastic process. And a special type of stochastic process is what we refer to as a martingale. And the stochastic process is a martingale if it satisfies two properties: that the expected value of the absolute value of the random variables is always finite, and the expected value of the random variable xt plus 1, given information about x0, x1 down to xt, is equal to xt only. That is the value that precedes the value of interest. That is, the expected value of tomorrow is just equal to the value of today. And again, that has to be true for all t in our temporal space t. Okay, so there's just some basic things that you definitely should know. Now what we're going to do is we're going to let our state space be explicitly defined to be equal to, let's call it S0, S1, S2, and so on. Let's define t to be equal to 0, 1, 2, and so on. And let's also assume that xk is equal to sk. So these are the values for which xk can take, right? That's what we refer to, again, as the state space. And we're going to assume that k, again, belongs to the interval 0, 1, 2, 3, and so on. So that's our domain set T. So let us first define what exactly is a Markov process. So definition. So let's assume that little s belongs to our state space S. Then x is said to be a Markov process, so x is going to be our xt that maps t to s, is Markovian if the following property for probabilities on these random variables xt is satisfied. That is, the probability that xm plus 1 takes that state s, provided that x0 is equal to s0, x1 is equal to s1, all the way up to xn is equal to little sm. This can actually be represented by ignoring all of the states preceding the value of today. That is, these can be ignored, and this can be equivalently represented as the probability that xn plus 1 takes the value of s is just conditional on xn is equal to sm. That is, if a stochastic process is Markovian, if you want to find the distribution of xm plus 1, the distribution of the variable of tomorrow, all you need to know is information about today, right? So the current state is all we need in order to forecast tomorrow. So some people will call that a Markovian stochastic process, and some people will refer to that as the Markov property of a stochastic process if it just happens to be satisfied. All right, so let's just look at a couple little subtle details that you might already know. So what we're going to do is we're going to define Pij to be a probability, so that means it's going to belong to 0 to 1, to be the probability, of transitioning from state I, actually from state j to state si. So state sj, that's where we're coming from, and state si, that's where we're coming from. That is, we're going from sj to si. Okay, so for example, let's assume that we have state 52 here. Let's assume that we have state 67 here. And let's assume that these are the only two states that we're actually focused on, right? So here's the state, and we can transition from one to the other, let's assume. Also keep in mind we can transition from state to itself. So this would, for example, be P6767, and this would be P5252. Okay. Now, when I and j are not equal to each other, that's where, the triviality becomes a little bit non-obvious sometimes. So here, what is this going to be? So here we're going to 52. So this is going to be P52 coming from 67. And this is going to be P, so where are we going? We're going to 67 coming from 52. Okay, so this perspective is usually referred to as the left stochastic convention, right? And that's used to define what we call left stochastic matrices. So generally speaking, what we have here is some state Sk that can go from state 1 to state 2 to state 3, all the way down to, let's call it state n, right? Where the size of our state space is equal to n. And Sk could be any one of these 1 to n, of course, right? So if we're defining based on this convention, then what we have here is that the sum from I is equal to 1 to m of Pij, this is going to be equal to 1, because it's summing across all values for which I can go to j or j can go to I, right, depending on which is your focus, right? So for example, if we're focused on Sk to S1, what is that probability? So where are we going? We're going to 1 and we're coming from k. And here we're going to 2 and we're coming from k. And all the way down to the last one, we're going from n and we're coming from k, right? So notice that the last index is always going to be fixed. That's going to be the place that we're coming from. And 1 to n is all the places that we could go to, right? So that means that the sum of this is equal to 1, because what you have here is some probability space sigma, and it's partitioned across your S1, S2, S3 down to Sn, for example, right? So that means by low total probability, the sum of those probabilities must be equal to 1. So if we think of this from the perspective of matrix entry notation, then this would just be referred to as a column sum of some particular matrix. So what exactly is that matrix for which we're summing the values in a column? So that's going to be represented by this fancy letter P. So this is going to be equal to P11, P12 down to P1m, and then we have P21, P22, all the way down to P2n, and that's going to continue all the way down to Pn1, Pn2, all the way down to Pnn, and that's obviously going to be an n by n matrix. And some people will refer to this as a left stochastic matrix. Some people will also call this a stationary stochastic matrix if these probabilities do not change as you progress through your time sequence, right? And again, notice that the sum across all of these is going to be equal to 1, regardless of the column that you focus on. And why is that going to be the case? Well, again, what is this coming from? So this is all the values for which we're coming from state 1. This is all the values for which we're coming from state 2. And these are all the probabilities for which we come from state n, right? For example, this is where we're coming from n going to 1, coming from n going to 2, coming from n going to m. And if we look at this other column here, that's coming from 2 going to 2, coming from 2 going to n, coming from 2 going to 1, coming from 1 going to 2, coming from 1 going to 1, and finally coming from 1 going to m, right? So that's the left stochastic matrix perspective. And the reason why we call it left is because what we're looking at is practically on the left-hand side of our matrix, we have a bunch of columns for which sum up to 1. So that's the convention. If you want the rows to sum to 1, that is usually called a right stochastic matrix. Right? So also, let's assume, so let's look at this particular matrix, and let's assume that this is a function of time, let's assume. So let's assume that Pij at some time t1 and Pij at some time t2 are equal to each other for all t1, t2, and our temporal domain t for our stochastic process x, right? So again, this, if all of our Pij's are constant, then we say that P is a stationary stochastic matrix. So those are just some of the bits of terminology that you definitely need to know before we start jumping into Markov processes. So now that we have some of the basics of terminology worked out for Markov processes, now let's jump into some of the little bit of details for computations. So let's define the initial state of our stochastic process, which is going to be denoted by x0, and let's define it to be equal to state sk, where sk is some value or state in our state space. What we're going to do in terms of notation to represent probability distributions of these random variables, keep in mind we're working on a discrete set for t, therefore, or a discrete set for s, therefore we're going to have probability mass functions for our random variables. So what we're going to do is we're going to represent p subscript x0 to be a column vector that's going to represent our probability distribution of x0. Now, x0 is going to be defined in a very special way, so keep in mind we're focused on sk for the initial state for x0. So when we look at the jth entry of this vector, what we're going to have is we're going to have 1 in position k, and we're going to have zeros elsewhere. So we're going to have 0, k minus 1, k minus 2, and k plus 1, k plus 2, and so on. Right? So elsewhere. Right? So that is going to be what our initial column vector is. Okay? So now our question becomes, well, how do we find the probability distribution for x1? Okay? So the probability for x1 is going to be defined by the following vector. So px1 is going to be equal to the vector defined by P, our stochastic matrix, multiplied by Px0, again, a vector. That's obviously going to be an m by 1 vector. So if we continue with this example, what exactly are we going to have? So obviously what we're going to have is our stochastic matrix P times our column vector Px0. Keep in mind this is going to have 1 and then zeros elsewhere. Right? So when we multiply a matrix by a column vector, we're obviously going to get a column vector. And which column vector are we going to get? Keep in mind what we're going to do is we're going to multiply rows by that particular column in a dot product fashion. Keep in mind, notice that the kth element of this vector is going to be multiplied by this particular kth element of that row vector, and it's going to be equal to 0 elsewhere. So if we focus on the kth column, compared to the kth row of that vector, these are the only values that are going to be multiplied by 1, and then we're going to add them up, right? In terms of zeros, zeros, zeros when we multiply, and zeros, zeros, zeros when we multiply, zeros, zeros, zeros when we multiply, and so on. So what are you going to have? Well, you're going to have your vector, by definition, px1, which is actually just going to be the kth column, so it's just going to be the kth column of p. Okay, so that's actually very trivial. The only non-trivial thing is the values, for example, px2, px3, and so on. So if we continue in this fashion, for example, what would px2 be? Well, by definition, if we consider a recursion, it's just going to be our stochastic matrix P multiplied by px1. But what is px1? Well, px1 is going to be P times px0. And keep in mind, matrix multiplication is associative. So this is precisely equal to our stochastic matrix P squared times Px0. And you can obviously see a nice little recursion, and you can use mathematical induction to justify this. But the probability distribution for xn, for example, is just going to be equal to P to the power of m times Px0. Right? So this gives us a nice iteration for that. Okay? So that's how you can find all of our probability distributions for all of our random variables in our sequence of random variables, i.e. our stochastic process. So we have a stochastic matrix coupled with the stochastic matrix P. So what happens when we combine these two characters together? So I'm going to represent the structure by C, and what we're doing is we're taking our stochastic matrix P, and technically that could be dependent on T, but it doesn't have to be. And then we're going to have our sequence of variables xt, which is going to map T to S, right? So we have a stochastic process coupled with a stochastic matrix. So what happens when we combine these two together? And it's very important, though, that if we want to find the probability distribution of xm plus 1, all we have to know is the distribution of xm, right? So the distribution of pxm, because that's all we have, right? And what type of distribution is that? Well, that is just the Markovian property. That's just the Markovian property, right? So we have a stochastic process that has the Markovian property. That means this stochastic process, xt, is a Markov process. And some people call the structure for which we would couple that Markov process with the stochastic matrix, some people will call this a Markov chain. So a Markov or a Markovian chain. Right? So those are some of the basics. So let's actually work through a numerical example just to make sure we get the basics of these terminology. So let's assume that we have a stochastic process whose state space contains 3 entries, S1, S2, and S3. Let's assume that the initial state of that stochastic process is state S2. And let's assume that we couple that stochastic process with a left stochastic matrix given by this 3×3 matrix P. So we're assuming that our initial state is equal to S2. So we should be able to state explicitly the probability distribution of x0 with respect to the state space S. So if we write that, what we're going to have is P0. I'm not going to write the x here because you know that we only have one variable here. So the probability that we're in state 1 is obviously 0, the probability that we're in state 3 is obviously 0, and the probability that we're in state 2 is obviously equal to 1 because that is guaranteed to be true here, right? So how are we going to get the probability distribution of P or x1, which I'm going to write as P1. So P1 is going to be equal to P times P0. And how am I going to find that? Where I'm going to take our stochastic matrix, 0.3, 0.6, 0.3, 0.4, 0.3, 0.3, 0.1, and 0.1, 0.4, 0.5, and I'm going to multiply that by 0, 1, 0. So if I multiply this row vector by this column vector, what am I going to get? So 0 times 0.6 and 0 times 0.4 is 0. And we're just going to be left with 0.3. Obviously, if I multiply this row vector by that column vector, everything is 0 except for 1 times 0.3. And if I multiply this last row by that column, what am I going to get? Well, 0 times anything is 0, and we're just going to be left with 0.4, which is obviously the second column of P, right? Which we've already deduced before, and that's obviously associated to the fact that we start in S2. Now, the next sequences are not usually trivial, but if you want to find, for example, the probability distribution for x2, that's obviously going to be equal to p times p1, or you could also do p squared times p0. As we already know, it's a Markov property, it's a Markov chain, therefore it satisfies the Markovian property, therefore you can do it either one of these ways. And once you actually do that, you're actually going to find this is approximately equal to 0.46, 0.23, 0.31, and you continue this process as far as you would like. So let's see if we can answer a couple numerical questions about this Markov process. So let's see if we can find what is the probability that x0 is equal to s2, and what's the probability that x1 is equal to s3, and what's the probability that x2 is equal to S1. So we already know the probability that x0 is going to take the value of S2. That's just going to be equal to 1. And then that's going to be multiplied by the probability that x1 is equal to S3, assuming that x0 is equal to S2. So that's just the product rule, times the probability that x2 is equal to S1, assuming that x0 is equal to S2 and x1 is equal to S3. Right? So keep in mind, since we're working with a stochastic process that is Markovian, we can actually rewrite this property for the probability of x2 is equal to s1 because the value of tomorrow only depends on the distribution of today, x1, and we actually don't need to include that particular condition. So we can rewrite this as the probability that x0 is equal to s2 times the probability that x1 is equal to s3 given that x0 is equal to s2 times the probability that x2 is equal to s1 given that x1 is equal to s3. So if you're correctly working with Markovian chains, you should only see adjacent indices for these conditional probabilities. All right, so what is the probability that x0 is equal to 2? Well, that's guaranteed to be equal to 1. And what's the probability that x1 is equal to s3 provided that x0 is equal to 2? So if we go back to our process, so what is the distribution for x1 provided that x0 was equal to 2? Well, that's obviously going to be equal to p times 0, 1, 0, which we already found to be equal to the second column of p, which is 0.3, 0.3, and 0.4. And we want the probability that x1 is equal to 3. And this is the distribution for x1. So the probability that x1 is equal to 3 is going to be 0.4. So 0.4 is going to be that value there. And the probability distribution for x2, given that x0 was equal to 2, was equal to state 2, was equal to p squared times 0, 1, 0. And that came out to approximately 0.46. 0.23, and 0.31. So what's the probability of getting state 1 in that process? That's obviously going to be 0.46, and those are going to be my associated probabilities. So once I multiply those out, assuming that I didn't do anything crazy, you should get something approximately equal to 0.172. All right, so let's do just another example just to make sure you can find probabilities with stochastic processes that are Markovian. So what's the probability that x1 is equal to s1 and x2 is equal to s2 provided that x0 was equal to s3? So we have a different initial condition. All right, so how are we going to find this? So we need the distribution of x1 and the distribution of x2, because keep in mind, this is just going to be equal to the probability of x1 is equal to s1, provided that x0 is equal to s3. Let's actually use parentheses, not brackets here. Just looks nicer, at least to me, but that's up to you. And then we're going to multiply that by the probability that x2 is equal to s2, given that x1 is equal to s1, and given that x0 is equal to s3. But we already know that this process is Markovian, so we just need to focus on x1. Right? So for this, what we need is to find p times x0, which is 0, 0, 1. And here we need to find p squared of 0, 0, 1. Or you can do, p times the distribution of x1. You'll get the same exact answer either way. Right? So once you actually work this out for this example, what you're actually going to find for p times 0, 0, 1, you're going to find that this is going to be equal to 0.4, 0.1, and 0.5. So what's the probability that we're equal to s1? That's obviously going to be equal to 0.4. And then once you do p squared times 0, 0, 1, you're going to get 0.47, 0.2, and 0.33 respectively. And want the probability of getting S2, so that's just going to be equal to 0.2. And once we multiply those two out, we're going to have 0.08 as our associated probability. So that's how you can actually do probability statements with Markovian processes. So an application of Markovian processes is what is called the Ehrenfest model, which is often seen in molecular diffusion and also thermodynamics. So let me briefly sort of sketch out what exactly the Ehrenfest model models. So what we're going to do is we're going to have two containers, which I'm going to call A and B. And what we're going to do is we're going to have some membrane in between A and B. All right, so this is a membrane. And we're going to have a bunch of particles in container A and a bunch of particles in container B. It's possible that container A contains no values, it's also possible that B contains no values, but let's assume for the sake of usefulness that both A and B contain at least one. So what we're going to do is assume that xk is the random variable that represents how many particles are in A, and let's assume that that's at time k, which is an element of our temporal dimension t. Right? And let us assume that at each time k, a molecule is randomly selected from the union of A and B, so you could choose either a particle in A or a particle in B, and whichever one you choose, it has to transition to the other container. That is, if a particle in A is chosen, it has to move to B. So the cardinality of B increases by 1, and the cardinality of A decreases by 1. And if a particle is randomly selected from B, then it must transition to A, so the cardinality of B decreases by 1 and the cardinality of A increases by 1. Now keep in mind, it's not necessarily obvious how many particles are in the system to start, so we're going to be taking that as a fixed known value. Okay, so let's assume that there's n total particles. So if there's n total particles, then you can say, okay, the number in A plus the number in B will be equal to m. And since we're representing xk to be equal to the number in A, that's going to be a random variable of interest. Obviously, you can focus on B if you really want, but it's technically equivalent. All right, so let's see if we can frame this from the perspective of probabilities now. Right? And we're also going to be assuming that the probability of any molecule being selected is the same as any other. So everybody is equally likely to be selected. So what are we going to have? So we're going to have xk, which is going to map t to s. And our t is going to be the set 0, 1, 2, and so on. And the state space, again, we're using xk to represent the number of molecules in A. So the smallest amount that our state space can be is 0, 1, 2, and the largest it can be is what? Take a guess. That's going to be capital M. All right, so that's the setup for our stochastic process. So now we need to see if we can build our stochastic matrix for this Markovian process, right? Because if you think about it, is this really a Markovian process? Well, if we have 5 molecules in A, and we're interested in the probability that at the next time step or tomorrow, we either have 6 or 4 or 5 or 10 or 17 or so. So it should be obvious that the number of particles in there on the next random draw is entirely dependent on how many molecules we have today. It's very similar to a random walk if you think about it. So let's see if we can formally phrase these probabilities. So what's the probability that xm plus 1, so the number of molecules in A tomorrow, is equal to the number of values in there today minus 1, assuming that xn has, for example, little xn in it. And actually, let's assume that that's little xn too, right? So these are numbers, and those are random variables. Right? So what's the probability that the number of molecules in A decrease by 1? So if the number of molecules in A decreased by 1, where was the molecule selected located? Well, obviously, if the size of A decreased by 1, that means the molecule that was selected belongs to A, right? So what's the probability that a molecule is selected from A? Well, obviously, that's going to be equal to the number of molecules in A at time t is equal to m divided by capital M. Okay? And keep in mind, this xn should be little xn, because that is just a number if it has already been observed, which we're assuming it has. Similarly speaking, what's the probability that xm plus 1 is equal to little xm plus 1, right? Assuming that at time t is equal to n, we had, again, xm. So if it increases, that means the molecule selected must have been belonging to the other step, which is the complement of xn over n, right? So that's obviously going to be equal to capital M minus little xn all over capital M, or you could equivalently write that as 1 minus little xn over capital M. Whichever one you feel more comfortable with is obviously perfectly okay. right? So obviously, since these probabilities of xn depend only on xn plus 1 only depends on capital M, we clearly see that this property, or this process, xt, is Markovian, right? So we have a Markovian stochastic process. Now we need to figure out, okay, if it's Markovian, maybe we can even build a Markov chain out of it, which will require us to have a left or potentially right stochastic matrix. So let's see if we can build what we call an Ehrenfest chain. So what exactly is an Ehrenfest chain? Well, obviously it's going to be a Markov chain associated to an Ehrenfest model, right? So let's see if we can write this. So an Ehrenfest chain. Because we already have explicit representations for our probabilities at different times, it's practically similar to a random walk. So let's see if we can actually build this piece by piece, right? So for example, if the cardinality of A is equal to 0, and let's assume that this is at any time t in t, then what are we going to have? So the probability that the cardinality of A increases by 1, we already know that's going to be equal to what? That means it came from the other entry. And keep in mind the probability of that being selected is going to be equal to 1 precisely. Because if we have 0 elements in A, there's no element in A to select. Therefore, it has to come from the other set. So that probability is guaranteed to be 1. And the probability that the cardinality of A decreases by 1, that obviously is going to be equal to 0, because if it's equal to 0, you can't select anything from it. So the case when A is equal to 0 is obviously trivial, and that's the smallest value that xn can take, right? So let's move up to the case where A is equal to 1. So when A is equal to 1, what are we going to have? So the probability that the cardinality of A increases by 1 is going to be equal to, so that means there's only one element in that set, right? So what's the probability that the cardinality of A decreases by 1, where there's only one element in A, so therefore the probability of that happening is going to be 1 divided by capital N, and everybody else is in the other set, so that's going to be capital M minus 1 over M, or 1 minus 1 over N. So the probabilities for that is going to be equal to, trivial things, 1 over N, and 1 minus 1 over M. So let's just do one more to sort of see if we truly understand. So what's the cardinality that if A is equal to 2, what's the probability that A increases by 1? And what's the probability that the cardinality of A decreases by 1? So if it decreases by 1, the probability of that happening is going to be 2 over N, and the probability that this is going to happen is going to be 1 minus 2 over N. All right? So these are the probabilities, and you should be able to see the pattern that regardless of the value of xm, 1, 0, 2, all the way up to m, we're always going to have these probabilities, right? So obviously we're going to have a little bit of patterns in our stochastic matrix. So let's see if we can sketch out what that is going to be. So xk can go from, for example, if we're at 0, we obviously can go to 1, or we can go from 1 to 0. We can also go from 1 to 2, or we can go from 2 to 1. We also can go from 2 to 3, or we can go through 3 to 2. Keep in mind, we cannot go from 3 to 3, we cannot go from 2 to 2, we cannot go from I to I, we cannot go from S to S, and we cannot jump more than one space if we do change, either up or down, right? So you should be able to clearly see that if n is equal to 3, the cardinality of our state space is actually going to be equal to 4, right? Because if our number of particles is equal to 3, well, maybe you should think about that for a moment before I tell you explicitly why the state space is equal to 4. Either the cardinality of A contains 1 particle, 2 particles, all 3 particles, or no particles at all, right? So our state space explicitly will be equal to 0 particles, 1, 2, or n, which is equal to 3, right? So if we have n is equal to 3, the cardinality of our matrix is going to be equal to 4. Okay, so our probability stochastic matrix will be a 4 by 4 case. So let's see if we can actually state this. So P is going to be equal to what? Right? So let's actually write this in a very organized manner. So this is going to be a 4 by 4 block. 4 by 4 block. Right? So we have 0, 1, 2, and 3, and 0, 1, 2, and 3. So what's the probability of going from 0 to 0? Well, that's obviously going to be equal to 0, 1 to 1, 0, 2 to 2, 0, 3 to 3, 0, and so on. So what's the probability of going from 0 to 1? That's guaranteed because there's no particles to decrease it, so it has to come from the other. So that's guaranteed to happen. And therefore, since that's equal to 1, all of the other values in that column are going to be equal to 0. Right? And again, what's the probability of going from 1 to 0? Well, the only way that that can happen is if the lonely little particle in A is selected, which has a probability of 1 over capital M. Right? So if that is 1 over capital N, its complement, which is located here, 1 minus 1 over capital N is there, and its complement is located here. Right? And then what is the probability of going from 2 to 0? Well, that's obviously going to be equal to 0. 3 to 0, that's obviously going to be equal to 0. 3 to 1, that's obviously going to be equal to 0. And I think that's all of the 0 probabilities, right? So what's the probability of going from 2 to 1? So you should be able to verify that that is going to be equal to 2 over capital M, which means that that's 1 minus 2 over capital M. And what's the probability that we go from 3 to 2? So think about it. What's that probability? That should be equal to just 1. Okay, so that gives us all of our probabilities, and we can state these in probability forms from the Markovian perspective. So what's the probability that, xm plus 1 is equal to 0, assuming that xn is equal to 1, so that's obviously going to be equal to 1 over m, and the probability that xm plus 1 is equal to 2, assuming that xn is equal to 1, that's 1 minus 1 over m. And similarly speaking, for a couple others, let's do, for example, if xn is equal to 2. So what's the probability that xn plus 1 is equal to 1, assuming that xn is equal to 2? So that means it decreases by 1. So that means one of those particles of 2 have to be selected. And the probability that xm plus 1 is equal to 1 more than 2, which is going to be equal to 3, assuming that xm was equal to 2, that's going to be its complement 2 over m because it came from the other place. Right? And let's look at this lonely little 1 in case you still haven't figured that out. So what is this little 1 here? So that's the probability that xm plus 1 is equal to 2, assuming that xn was equal to 3. Keep in mind the number total of particles is equal to 3. So that means the other container does not have any particles, which means the only particle to randomly be selected must come from A. Therefore, it must decrease by 1. Therefore, this is an absolute certainty. Right? So this is the type of matrix that we have. Now let's look at a couple geometric things about this matrix. Notice that we have a primary diagonal of all zeros, and then the only other non-zero values we have are located on the secondary diagonals, right? So this matrix is sometimes referred to as a tri-diagonal matrix, okay? So let's look at a numerical illustration of what this actually looks like, but instead of doing n is equal to 3, see if you can build the matrix where n is equal to 4 before I show you the correct answer. So let's assume that we have 4 total particles across both of these containers with one membrane separating these two. So what is the size of our stochastic matrix? Well, P in this case is going to be 4 plus 1 by 4 plus 1, which is going to be a 5 by 5, because the state space is going to be 0, 1, 2, 3, and 4. Right? So once we build our stochastic matrix, it's going to have a very similar property to our 4 by 4 case. So we're still going to have zeros on our primary diagonal, so 0 there. Underneath that, we're always going to have 1, and then 0, 0, 0. And then over here, we're going to have 1/4, and then 0, and then its complement, 3/4, 0, 0. And then we're going to have 0, and then 2/4, primary diagonal 0, and then 2/4, and then 0. And then we're going to have 0, 0, 3/4, 0, its complement. And then we're going to have 0, 0, 0, 4/4, and 0. I'm not reducing my fractions just in case you haven't seen the pattern quite yet. So technically that is 4 over 4. Okay, so what we have here is our tri-diagonal matrix. So there is our lower diagonal, there's our upper diagonal, and here we have our lonely diagonal of zeros, right? So this is sometimes what people call the Ehrenfest matrix of order 5, or you could also call it order 4, depends on what your focus is on. Right? So that is our stochastic or left stochastic matrix. We already know how our stochastic process is going to be set up. So let's suppose that we start with, or we have, n is equal to 3. And let's assume that we have, let's see, what exactly do I want? So we have 3 total molecules. Oh, no, we assume that we have 4 total molecules. And let's assume we have an initial amount, in A, to be equal to 3. Right? So this is A and this is B. When T is equal to 0, practically what you have here is 1, 2, 3, and there's our lonely little fourth. Right? So what is the probability distribution for x0, right? So the probability distribution for x0 obviously is going to be equal to what? So this is going to be represented as 0, 1, 2, 3, and 4, keep in mind, okay? So what is the probability that we have 0? Obviously that's 0, 1, 2, 3 is guaranteed, that's our assumption, and then finally 0. And then we can say, okay, well, what is the probability distribution for x1? So that's going to be equal to our stochastic matrix times p0. And we already know how to multiply these things out. So what is this going to be? So this is going to be equal to the 4th column of our stochastic matrix P, right? This is going to be equal to the 4th column of P, which is going to be equal to 0, 0, 3/4, 0, 1/4. That's the typical trivial one. And then comes the fun ones. So what's the probability distribution for x2? So this is going to be equal to either stochastic matrix times P1 or stochastic matrix squared times P0, which we're usually given up front, right? And you should be able to find that this is going to be equal to 0, 0.375, 0, 0.625, and then finally 0. And then similarly, how would you find x3? Well, that's just going to be equal to p cubed times p0. You can actually find this is going to be approximately equal to 0.090, 0.75, 0, 0.16, and you can continue this process as long as you want. Now, one very interesting thing that you should think about is the following. Firstly, note the structure of this vector and this vector. Notice that the zeros switch between even and odd indexed entries. Can you think about why that is the case? If you need a little bit of a hint, recall the structure of how random walks usually, go, right? Because we can either go left or right. We can't stay where we are, right? So the number of molecules in each of these containers obviously increases by 1 or decreases by 1. It cannot stay fixed. That's pretty much why we're sort of bouncing back and forth, because we're not allowed to stay fixed, okay? So that's practically the little pattern. So it's obviously clear to see that even if we exponentiate this p infinitely many times and multiply by p0, it's still going to alternate between these two different structures. But in terms of long-term behavior, we'll get into that a little bit later, but these are some of the basics that you definitely should know when it comes to Markov processes, and also how you can apply this to solve Ehrenfest processes, which are very useful in molecular diffusion. Hope you enjoyed this video, and I'll see you in the next one. Take care.